weather forecasting uses data, and actually weather forecasting, not to brag, but used data before it was big, and we continue to use it to great benefits. So I hope to show you some of the ways that we use data and large big data sets to improve weather forecasts, but also I wanted to share some of the learnings that I've seen from this field of science from using data and how not to use data as well. So I wanted to start this story by saying that weather forecasts are getting better. This is a little graph that's showing forecast skill, so the higher the better, and going back from 1980s to pretty much now, or 5 years ago. And the different colors show different forecast day lengths. So the blue one is looking at the third day, so looking 3 days ahead. What's the skill of that? Red is the 5 day ahead forecast, and the green is the week ahead, and the bottom yellow line is the 10 day ahead. So you can see that in just 30 years, or less than that, so just over 30 years, we've gotten as good or even better at predicting the 5 day forecast as we were 30 years ago at predicting the 3 day forecast. So that's a huge benefit. This is global average, so this is not just a particular place, but this is produced by the European Centre of Weather Forecasting, who are the best, admittedly, at predicting the weather. But you'd see similar things for the Bureau of Meteorology and any other national weather centre. This is a plot showing the last decade and also projecting a few years from now at looking at how much data is sort of consumed. And this unit is in zettabytes, which is 1 billion terabytes. And so it's a lot of data. And you can see that the shape of it is exponential. And this is, I think, encapsulating what other people, or what a lot of people call the big data sort of revolution. This is a plot showing now weather data counts over the last 40 years. And this is the red lines are showing the counts of 2 very popular weather observation or weather data that we collect. Brightness temperature, which tells you sort of the height of a cloud or the temperature of that cloud. And surface pressure is also very useful for predicting things like fronts or abrupt changes in the weather system. But this is a logarithmic scale, so the red lines are showing since the 1970s, we've seen 2 orders of magnitude in the amount of data that we are recording from the weather system in both, or slightly less in surface pressure. This big jump is one of the big data revolutions. What are weather data? So in the early 1900s, or perhaps earlier than that, and all the way up to the 1970s, we had some conventional data that we recorded. So if you were operating an observation station, you might have a Stevenson screen, which is this little box that has a thermometer inside and records the atmospheric temperature without affected by the sun. You might have an anemometer that spins around, and that measures the speed of the wind. You have weather socks that blow opposite to the wind direction. All of these are weather data, but perhaps more conventional ones. Then in the last sort of 100 years, we've also developed things like radar, which can actually bounce things off clouds and rain to tell what's happening there. We can put things on planes and put similar instruments like the ones I described at the weather station that can operate in higher speeds and can actually measure things as the plane goes up and down. But the big revolution that happened in the 70s and 80s and since then is these big satellites that we've put up in the sky. So these satellites do something different. They don't measure in situ, meaning they don't measure what's happening in the space that they're in, because we don't actually care about the weather too much up there. But they put these amazing instruments that can actually measure things from very far away from them. And then we call that remote sensing. The technologies that happened in remote sensing allowed us to not only collect different data to what we used to, but huge amounts of it. So they can actually look at huge swaths of the planet, significant portions of it in any given day, and transmit that back to people like me or weather stations that are, meteorological forecasting stations that can make use of that huge amount of data. So we've seen that over the last 30, 40 years, that huge data revolution, but there is still one that is happening again. It's always happening, but we're seeing more different types of satellites. So this is a CubeSat on the top right there that is about the size of a Rubik's Cube. And it's a new type of satellite. It sits very much lower in the atmosphere than the satellites that I have up there that maybe you've seen or heard of. And they record different types of data. They record video and photos, stuff that we haven't really made huge use of in the weather modeling community. But they also will be much more numerous and cheaper. So you can launch these, you can launch 100 of them at once on one sort of launch. And you can, perhaps we'll have ways of launching singular ones. One group that is focusing on trying to put more of these in the sky is ARS. You may have heard of the Australian Research Space Exploration. Very awesome acronym. They're not actually focused too much on exploring outside of our planet or even outside of our even to the moon, but their focus is definitely on putting more observing stations or more observing opportunities into our atmosphere, mainly for weather forecasting, but I mean, the opportunities are boundless. There's also new unconventional weather instruments. This one might not look too familiar to you, but I guarantee that all of you probably have one on you and have for the last 5-6 years. This is a microchip, phosphorus microchip that senses atmospheric pressure in your phone. So this is the model from the iPhone 8, but very similar ones exist in all smartphones. We don't use these data yet, but we very will soon for things like unconventional prediction of atmospheric pressure, and use all of you as our moving weather stations. Here in Melbourne, we all know that the weather can change very rapidly, and you can't tell me that recording even on your fancy satellites for the last 10 minutes what the atmospheric pressure is, that you'll be able to tell me what it is in 2 hours time or even 2 days time. Some people are interested in weeks ahead. So there is something that's missing from this story, and that's something that I'd like to introduce, which is weather models. So weather models, one of which is sort of shown here in a schematic, solve what we call an initial value problem. So they take a now and then they transport that into the future using some physical law or mathematics, some understanding that we have to prescribe, and weather modelers will code. They'll have to code it into some software system, but it takes a now, an initial, and it takes it into the future. And the way we do that is by splitting up the whole planet all onto small little cubes and grids. And we say within that little grid, we know that the laws of physics have to hold, that atmospheric mass has to be conserved, energy must be conserved, and we know a lot of things about the flow of atmospheres and oceans, and we can put them into mathematics very carefully and tell a computer how to solve those differential equations on that grid. So each one of those squares we solve it individually. We tell what the neighbors did, and with that we can integrate time, and we can actually take our present into the future. So the way we're utilizing information from the past is my field. This is called data assimilation, and it's really about using data to correct the models and keep them on track with reality. So very briefly, the previous forecast in this schematic, this is sort of like an example of how data assimilation works, but you have an old forecast that maybe we did yesterday for the future. But in that time, since yesterday, we've recorded all these observations throughout the day of what actually happened. And it often doesn't match what we predicted it would have exactly yesterday. So what we can do is actually use both sets of information and come up with a computational optimization problem to optimally choose what's the most likely analysis. We call it an analysis. It's basically a corrected forecast that best fits what happened and what we thought might happen. And through this, we do this through we call it a 4-dimensional problem, because we're actually solving it over time. We're not just coming up with an initial condition for our next forecast that best fits the data that has happened, but it also, of it happened since the previous forecast, but it also uses all of the observations that have come in since then. So this sort of completes the picture. With more data from the past, we can actually get a better corrected forecast. The problem here is that we're never going to be able to observe enough to constrain our models. Just if you thought that the picture was easy and that we had so much big data, we're actually not, we don't have enough. So these models I showed you, they have these little grids, and if you split up and you count exactly how many cubes there are within this whole global grid, you get something like 10 to the 9. So that's 400 billion, 4 billion points, and that's a lot, 400 billion. And that's only every 10 minutes. That's only every time step of the model. For comparison, in a day, we record something, even with the satellites, only a fraction of that, so a tenth of that. And that's in a total day. So to do any sort of forecast, to compare the numbers, you'd have to times them by how many 10 minutes there are in the whole day. So we're not there yet. In fact, we're only recording or observing less than 1% of the model that we're trying to predict. So we've got an under-constrained problem. This in mathematics is a problem with underfitting. You don't even know what you don't know. So this is the problem, and it's not going to get better. It's actually going to get worse. As we make these models more sophisticated, we want higher resolution. We want to make those cubes smaller so we can represent what's going to happen in my suburb or in my backyard. And that's called the curse of dimensionality. So as you get bigger, as you refine these models, your number of grid points that you want to constrain in your model increases with the cube of that resolution. So we're going to have to at least increase the data, not just by times 100, but we have to do it also with the cube of our model grid. So it's not all doom and gloom. We do make improvements. Big data does help. So there are things you can do by improving your models using data. This is a new sort of, well, it's not new anymore, but data-driven models, things like neural networks, deep learning, machine learning in general, is a huge opportunity for the big data revolution. We don't have to come up with these models anymore. We can tell a computer to do it. The way it works in weather forecasting is that, well, in general, there's sort of like algorithms that simulate your physical model, or emulate rather, by using a training data set and telling your computer to figure out the rules itself. You don't need to use the Navier-Stokes equations in physics to tell you don't need to teach your computer that, but rather you just show it a bunch of data and it'll infer it itself. Neural networks do this with a hidden layer scheme where they have non-linear activation functions between what's input, so that would be a training data set, and your output, which would be your prediction, for example. And they offer huge opportunities, but unfortunately, weather systems are too complex. You can't actually get enough data to train a computer model to do it well enough. And if you did, it wouldn't do it fast enough. Also, global warming is a problem. It's like the understatement of a century. Global warming is a problem, but it's a problem specifically for this because you need training data that's already happened to train your model. And if you wanted to predict something like climate change, you don't have a training data set that fits your global warming scenario. It's an unprecedented situation. So you can't do things that are involved with non-stationary, what we call non-stationary problems. Another reason why atmospheric weather modeling, and this might be applicable to all of your graduate research, is that with chaotic systems, where is a system where you have high sensitivity on your initial conditions. So anything that involves human decision can be considered a chaotic system. You may have heard of the butterfly effect, where you think about small changes creating big, unlikely outcomes in time. That was actually coined by a meteorologist who was describing the weather system and the Earth system in general. So this is a huge problem for data models. Another thing is, we can't just keep wantonly saving and collecting all this data in hope that we can improve our research or improve our outcomes. There's a problem called data latency. The more you collect and try to process, the more you have to be able to feed through your computer system. And this poses a huge challenge as an input-output sort of computational challenge for high data volume models or methods. And for weather forecasting, we've got to do this. This is a problem. You can't just have long computational systems. If you wait for all the data to come in from the other side of the world, then you might miss out on your next forecast. And we expect 4 forecasts a day, and these forecasts are really important for a lot of people. Another question you might pose is when will researchers be replaced by machines? I think I can say that big data offers huge opportunities as a tool for researchers, but it's not going to solve our problems, particularly when we have complex systems, and we all work with complex systems. Data has some serious holdbacks. I think it's clear that we need to use the tools, use big data as a tool, and although a bad work person might not blame their tools, a bad scientist definitely can't get away with blaming their tools, but a bad scientist or a bad researcher would ignore their tools and not embrace one that offers so much benefit. So I'll leave you with that, and if you're interested in my research, please come and talk to me.